All right, 1.4. We are going to actually transform functions today. Before we just learned, what's a, b, h, and k, what do they do, where are they in a function, what do you do when they're on the outside versus when they're on the inside. Today we're actually going to be given a function and we're going to transform it and graph it. We love graphing. So before we do that, there are two functions we are going to focus on transforming today. But just know you can transform any function. They all transform in the exact same way. So in theory, I won't do this, but I could give you any function and you would be able to transform it because every function has an a, b, h, and k, and they all do the exact same things. We are going to first transform the absolute value function. That's right here. F of x equals the absolute value, that's the vertical bars, absolute value of x. This is called a parent function because this right here is the father or mother of all absolute value functions. Any absolute value function you plot on a coordinate plane starts by the parent function. That's the beginning, the simplest, most easy form of it. It doesn't have an a, b, h, or k. It doesn't have any of the values. It's just the parent. So, who remembers what an absolute value does? Do you remember? This is the definition of an absolute value function. It is how far a number is from 0. How far away a number is from 0. For example, the number 5 is how many spaces away from 0? 5. Right? The number 27 is 27 away from 0. Here's where it gets weird. Let's look at negative 5. The number negative 5 is how far away from 0? 5. Negative 200 is 200 away. By definition, it's how far a number is from 0. So it's always a positive number. You can think of it as when you put something in, it better come out positive. Okay, so here is where a, b, h, and k would be inside of a absolute value. A, b, h, k. See them? A, b, h, and k. Always in that order, always in the same spots as yesterday. A, b, h, and k. Remember, A and K are on the outsides, B and H are on the insides, which is important because the insides do that tricky little flippity flip, where the outside you just look at them with your eyeballs. So let's graph the parent function of an absolute value. When you plug in negative 2 into the absolute value, what comes out? How far is negative 2 from 0? 2. What happens when you plug in negative 1? What comes out?
1.
1. When you plug in 0?
0.
When you plug in 1?
1.
When you plug in 2? Boom. Those are 5 points on the absolute value function. Let's plot them. Negative 2, 2. Haha, 2, 2. Negative 1, 1. 0, 0. 1, 1. 2, 2. Connect your dots. Nice straight lines. The absolute value parent function looks like this. It looks like the letter V for absolute value. That's how I remember. Absolute value, it's shaped like a V. This is always your starting point for absolute values. You start at the parent function and then it can become any other absolute value function using just 4 values, A, B, H, and K. So what we're going to do now is we're going to look at an absolute value function that has an A, B, H, and K and figure out what they do and how to graph it. So I am going to skip the quadratic and we're going to do example 1 on the inside and then we're going to come back. Open it up. Make sure that table is in front of you because we'll be using it in just a second. Page 13. example 1. When you look at example 1, there's a lot going on, but is it obvious that this is an absolute value function? Right? It should be, because what does it have? Do you see the absolute value bars? If you see those, you should automatically think, oh, this is absolute value, so it's the shape of a V. I see the X, I see the absolute values, but I also see a lot of other things going on. I see a 3 in the front, I see the 1/2, the -1, and the -2. There's a lot going on. A lot going on, and these are our A, B, H, and K values, right? Always in the same spots, always right in order. So let's start with A. Our A value is 3. It always is in the order, A, B, H, K. So that means 3 has to be our A value. 3 is our A value, and now we need to go look at our table on page 13 and figure out what happens when the A value is 3. There's 3 possibilities. It will either vertically stretch, vertically compress, or reflect across the x-axis. Which one will it be? Use your table. Because you don't know how to use the table. Is it any good to you? No. So practice using it right now. We can help you use it. Yes. So when you look at A, so is A greater than 1? Yes, so it'd be vertical stretching. Yeah, so you just write that next to it. So when you're looking at your table, here's what it says in A. It says, if A is greater than 1, it vertically stretches. Then it says, if A is between 0 and 1, it would compress. If A is negative, it would reflect. Which one is it? Greater than, between, or negative? Greater than 1. So this will vertically stretch. Vertically stretch. That 3 floating out in front of our absolute value will vertically stretch. It's like if I grab your toes in your arms and we just stretch you tall. That's what we're about to do. You know that like old medieval torture device where they like bind their hands and their legs and they crank and it pulls you apart? Well, that's what we're doing to the function. Okay, what is our B value? And be careful. See what I did there? Be careful. That's our B value. It's not 1/2. It looks like 1/2, but what do we have to do to it? It is being divided. We have to flip it to multiplication because it's on the inside of the absolute value. Inside of the function, we flip. Right now it's 1 divided by 2. We need to flip it and make it multiplication. So it's going to become just 2. And again, practice using your table right now. Go to the B in your little table. What happens when the B value is 2? The table on page 13. When the B value is 2. Yep. Greater than 1. 2 is greater than 1, so it would be a horizontal stretch.
Oh, God.
B value. Horizontal stretch. B is greater than 1. Horizontal stretch. On to the H value. The H value is our light blue. It's on the inside. It looks like we're subtracting 1, but the opposite is to add 1. So positive 1. The H value is positive 1. So you go to your table on page 13, you go look at h value, and only two things can happen. Either it goes right or it goes left. If it's a positive 1, which way do we go?
Right.
Right 1. It will go right 1 unit. Last but not least, our purple at the end, or pink. This is on the outside. It's your k value. You look at it with your eyeballs and you write it down. It's -2. Go to your table. Look at k value. When your k value is -2, where's it going? Down 2. Yep. Down 2. 4 things are going to happen. Vertical stretch, horizontal stretch, it will slide to the right 1, and it will slide down 2. All of those things are going to happen, but we always start with the parent function. This first table, this is for the parent. This is our starting point. This is where we start, parent function. Okay, we just did the parent function, didn't change. When we plug in -1 into the absolute value, what comes out? A 1. When you plug in 0, when you plug in 1, 1. This is the start. So let's graph the start. -1, 1, 0, 0, 1, 1. Since this isn't my final answer, I just do a dotted line. Oh. Here's my parent function, the absolute value of x. That's where we're starting. We're going to take this graph and we're going to vertically stretch, horizontally stretch, go right and down 2. Yes. Yes, where we got these y coordinates is the parent function, which is right at the top of this table, is absolute value of x. When you plug in the x value into there, when you plug -1 into the absolute value of x, by definition, anything that goes into the absolute value just comes out positive. So when we plug in -1, it comes out positive 1. When we plug in 0, it comes out 0. When we plugged in 1, it would come out 1. If we plugged in -20, it would come out positive 20. So we're just using that parent function, plugging in the number to get the y values. Good question. Okay, let's look at our first table. Watch very carefully. This right here tells you what to do. This middle table is for the a and the b values. We're going to multiply our x values by b, and we're going to multiply our y values by a. They're kind of flip-flopped, right? I wish it was a and then b, but it's b and then a. That's just the way it is. Our b value changes our x values, and our a values change the y values. And it's really easy to accidentally flip it. It happens to me too. My brain wants to do a and then b. So I take a second and write down what I'm going to do under my table. My b values are all going to get multiplied by my x value. So I look at my b value and I write that underneath. I'm going to multiply. I'm on the highlighter still. I'm going to multiply by 2. So I just write that underneath, just so my brain doesn't get mixed up. My y values are going to get multiplied by 3. So I just give myself a little note. Hey, multiply these by 3. You always look at the last table you made to help you out. So all of these x values multiply by 2. All of the y values we multiply by 3. So let's do it. What is -1 times 2? Yep. What is 0 times 2? And what is 1 times 2? 2. So what you just did is you just did this. You just horizontally stretched the absolute value. By multiplying the x values by 2, we've stretched it horizontally, like this. Pulling Laffy Taffy. Now we're going to do our vertical stretch by multiplying all of the y values by 3. So 1 times 3 is, 0 times 3 is, and 1 times 3, 3. And now we're going to graph our progress, all right? Here's where it started. Let's graph what the a and b look like. So -2, 3, 0, 0, and 2, 3. Now, our graph looks like this. Didn't change a lot, but it did change a little. We vertically stretched it and horizontally stretched it. We pulled it up and then pulled it out. So far we've done our A and we've done our B. Our last table is for doing our H and our K. And we always base our X and Y values off the last table. So we don't start all the way back at the first table. Now we're using these values that we just made. So our H and our K value are responsible for sliding the graph left and right or up and down. So H, the H value goes with X, and the Y value and the K value go together. And the middle table is multiplying, because remember our A and our B value are multiplying. Our H and our K value will be adding or subtracting. So what was our H value? 1. Positive 1, so we're going to add 1 to all the X values. Our K value was -2, so guess what we're going to do? Subtract 2 from the Y values. And that will give us our final answer. This table right here is always our final graph answer. The middle one's like we're halfway there. The last one is final answer. So let's add 1 to all the X values. Add 1 to -2. Add 1 to 0. Add 1 to 2. Okay? So what did we just do? We moved the whole graph right 1. The Y values, these are going to move it down. Subtract 2 from everything. 3 minus 2. 0 minus 2. Yep, and 3 minus 2 again. Okay, so this will be our final answer, our final transformed absolute value. So -1, 1. We got 1, -2. And we have 3, 1. I connect with the solid line because it's my final answer. Boop. There is my transformed absolute value. Final answer. And all 4 of those things happen. Vertical stretch, horizontal stretch, and move to the right 1 and down 2. Look, it went right 1, down 2. It got wider and it got taller. And that is how you transform any function. We just happen to do it to an absolute value. But no matter what function I gave you, it would be done the same exact way. Now we back it up. Ready to back up? Back to the front side, we have to do the quadratic parent function and then transform it. Just like before, this is our parent function. It's the simplest quadratic that exists. What makes it a quadratic is that it's x raised to the second power. That's what makes it quadratic. Any function with x to the second power as your biggest exponent is automatically a quadratic. Okay? But this one's the simplest. It doesn't have an a, b, h, or k value. We haven't added anything fancy to it. Just like before, and you'll notice the pattern, look at our a, b, h, and k. Aren't they all in the same exact spot? They're always in the same spot. I could give you any function, put it in front of you, and you could be able to be like, oh, there's A, B, H, and K. They're always in those 4 spots. Every time. Always in order. A and K are always on the outside, and B and H are always on the inside. A and K, you always keep the same. B and H, you always flip their operations. So let's figure out, what does the original look like? So let's graph the parent function. Again, to find these y values, we're plugging our x values into the function. When I plug in -2 in for x, what I get out is -2 squared, the power of 2. Which means -2 times -2, which is 4. -2 times -2, a number times itself, would be +4. What would -1 times -1 be? 0 times 0. 1 times 1. 2 times 2. Yep, we're getting those y values by taking these x values and plugging in for this x. Which means we're just squaring each number. Yeah. Well, what happens when you do a -2 times a -2? It becomes, yeah, when you square a negative number, they become positive because you're doing a negative times a negative. Yep, that's a good question. Okay, let's plot it. -2, 4, -1, 1, 0, 0, 1, 1, 2, 4. This bad boy's got a curve. We like curvy graphs. Straight ones, like the absolute value. Straight B.
How? Explain it.
How what?
Say it out loud. We'll talk about that.
Alright, are we good? Are we ready to do our second example and call it a day and done with notes for the week?
Look, it's Tuesday, right? Our test on Friday. We cannot take a break. I'm going for it. I promise you.
We're not going to take a break. We're going to keep practicing this stuff.
I can't do that.
We're done learning new things.
That day I missed last week, I messed me up.
Why would you just do that?
Alright, final example. Example 2. On the inside, the one we haven't done yet. This is an example of a quadratic that has been transformed. How can you tell this is a quadratic by looking at it? It has an x and it has an exponent of 2, a power, a square. Because this has an x and a squared, we know it's quadratic. We also know that a bunch of random nonsense has been added. We got this weird negative in front. We got the 2. We got the 3 on the inside. And we got this +2 at the end. All these are values that we've introduced to the parent function that are going to change the way it looks. So which of those is my A? Yes, it's easy to think it's the 2. There's actually a -1. Yeah, whenever you see a negative in a parenthesis, there's always an invisible 1. But mathematicians are lazy. They don't like to write 1s. Because what happens when you multiply by 1? Nothing.
So it's -1.
What would the B value be?
2.
Eh.
Actually, no, right.
What do you do to it?
You divide it, so it's 1/2.
So it's 1/2. It looks like 2, but we flip it and make it 1/2. H value looks like +3, but it's actually -3. K's on the outside, it's boring. You just look at it with your eyeballs. It's just 2. Okay, so there's our 4 values. But now's the important part. Okay, I'm proud of everyone in the room for knowing your A, B, H, and K, but we need to know what they do. So go to your table. What happens when the A value is -1? Does everyone see that it reflects across?
Right?
It reflects across the x-axis because what is it? It's
Oh, if it's negative.
if it's negative, it reflects.
How do I feel it's greater?
It's going to reflect across the x-axis, which means We know the parent function starts by looking like this, like a smile. If it reflects across the x, now it's a sad face, a frown. So our final answer should be a quadratic that points down because of that -1. Now what's our b value going to do? Horizontal compression. Can everyone see in your table why 1/2 b value is a horizontal compression? Horizontal compression is like our graph went on a diet because it's about to get skinnier, yeah? Smaller, this way. Okay, h is -3. What does that mean? Left 3, yep. I know there's a lot of fancy words there. You can just say left. Horizontal translation just means a slide to the left. Means its shape doesn't change, but we can just say it means left 3. And k being 2 means it goes up how many? Up 2. Alright, perfect. Now we do just like what we did before.
You knew you were wrong about that.
We need to start with our parent functions. Help me fill out the parent function values. What happens when I plug in -1 into x squared? 1. When I plug in 0. When I plug in 1. 1. 1 times 1. Okay, so here's our start. We plot 1, -1, 1, 0, 0, 1, 1. I like to just do a dotted line because this is just my start. Okay, so that's what it starts looking like. And now one step at a time. First, we do our a and our b values. But what do I like to do first before I start writing numbers down? I like to write underneath what I'm going to do. I'm going to multiply b and x together. So I'm going to go look for my b value. So I'm going to multiply by 1/2. And then I know my y values. I'm going to multiply by a. So I go look at my a value. And I'm going to multiply by -1. I like to just write that down because my brain automatically tries to do a first and then b. And sometimes writing it down helps my brain not accidentally do things in alphabetical order. So, let's multiply each of our x values by 1/2. What is -1 times 1/2? -0.5 or -1/2. Now we got 1/2 times 0, which is 0. And then 1 times 1/2, 0.5 or 0.5, both perfect. So that's multiplying all of my x values by the b value. Now we multiply all of the y values by the a value. So multiply them all by -1. So what do they become? -1, 0. Yay. Remember, these are all based off of this table. There we go. Now let's plot. This is going to do a reflection and a compression. So it should flip to pointing down and be squished. Squeezed, yeah. So let's see if, hopefully that's what happened. So we go over 1/2 to the left and down 1. Then we go 0, 0. Over +1/2 and down 1. Again, I'm not done yet, so I do a dashed line. And did it reflect and get squished a little bit? It definitely looks like it did. And now all we have left to do is what? Slide it 3 to the left and up 2. Yeah, bro. Okay. What was our h value? That goes with x. So we're going to subtract 3 from x, and what are we going to do from our y values? Add 2. Okay, so we just have to subtract 3 from the x, add 2 to the y. Okay? So negative 0.5 minus 3 should be negative 3.5. 0 minus 3 is negative 3. And 0.5 minus 3, negative 2.5. All the k values we're going to add to. What is negative 1 plus 2? What is 0 plus 2? What is negative 1 plus 2 again? 1. This graph is our final answer. We go to our table. We go over to the left 3.5 and up 1, right there. We go over 3, up 2, right there. And we go over 2.5 and up 1. This is our final answer, so I'll do a solid line. And look at that. Final answer of our transformation. We've reflected it, compressed it, and then moved it left 3 and up 2. Can you see how it all happens? Like boom, 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 boom. And that is how you can transform. We only did absolute values in quadratics, but any function, they all transform the same exact way. I could put any function, a function you've never seen before. You could make the parent function and graph the rest.